Alright, so we're looking at polynomials here, and the first question is just to identify the degree of the polynomial, and the degree is just the highest power of x that you see. And one thing that is important here is, for something to be a polynomial, the only powers of x that are allowed are positive integers. So here we see all of those qualify, so it is a polynomial. If you saw like a negative integer or a fractional exponent, that could happen either by dividing by a variable or say taking the square root of a variable, it would fail to be. But this one is. We see the highest power of x there is 6. So this one is a polynomial and the degree is 6. You can also talk about the degree of each specific term. So this polynomial is said to have 3 terms, a degree 6, a degree 4, and a degree 3. So you can talk about the degree of each term too, but when they speak of the degree of the polynomial, they're just talking about the highest power. Okay, one important thing about polynomials in terms of like graphs, domain, and range and things like that, we can talk about over here. Let's say properties of polynomials or polynomial functions. So an analysis professor I had in graduate school, he always described polynomial functions in some sense as being the nicest functions in the universe. So one thing that we can say about them is that they are continuous. So if we look at the graph to the right, we immediately can recognize that that is not a polynomial because it's not continuous. Remember, one way to think about continuity is it can be drawn without picking your pen up off the paper. So this one has a big gap. You'd have to draw it in 2 pieces, right? So you'd have to take your pen off the paper. So we know this isn't a polynomial, but in terms of polynomials, we can also talk about their domain. Their domain is going to be all real numbers for every single one. You can always plug everything into them. The range, not necessarily. If it's an odd degree, it will have domain or range all real numbers, but if it's even, it will not. If you think about, say, y equals x squared, that's a parabola that opens up. So you're missing half the possible real numbers. You're only getting the non-negative ones there. Other things that you can say about them too is they're smooth curves. So this gets more into like calculus, and that's one of the reasons you think about them as some of the nicest functions in the universe. They're actually smooth. They don't have any jagged points in them. In the language of calculus, we would say that they're differentiable. But for now, if you think about the picture, they're just smooth. Something that would be a jagged point would be like y equals the absolute value of x. It comes to a sharp corner right there where it meets. So those are some of the properties. Of course, there's others, but so we know that's not a polynomial. Okay, leading coefficient test to determine the end behavior. So we can break down the end behavior into 4 cases. And the only thing you need to understand to describe the end behavior is the leading term, so the term with the highest power of x. So the end behavior of polynomials. So, in general, you would write a polynomial like this. You would say given p of x equals, say, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a bunch of other terms plus a1x plus a0. So when you write a polynomial like this, those a's with subscripts in front are all real numbers, and x is your variable, and then the other ones are powers. So, but the end behavior, that's all we have to care about, is actually that leading term. So this is a n minus 1. So, the end behavior is determined by the leading term which is an times x to the n. It's determined by looking at two things. You look at the leading coefficient, which is a sub n. You care about whether that's positive or negative. And then you also care about the degree of the term, which is n itself. And you care about whether that is even or odd. So what happens, well, there's 4 cases. So, 1, you could have a sub n is positive, and n is an even number. And we're just trying to think of what the graph looks like at the ends, like which way the arrows of the graph point. So, in this case, it would look roughly something like y equals x squared. Eventually, both sides will point up. A bunch of stuff can happen in the middle, but eventually you get both sides going up. So both sides rise. And then we could think about, well, if a sub n remained positive, so we could have a sub n is positive, but you have the power n being an odd number, you could think about a graph like y equals x cubed. Then what happens then is it falls to the left, but it rises to the right. So falls left and rises right. So if you look at this specific example right here, we only have to pay attention to 2x to the 5th. So 2 is a positive number, and 5 is an odd number. So we are in case 2. We know that this answer is going to be falls left and rises right, which is choice C. So that's going to be the choice here. But let's still walk through the remaining 2 cases where a sub n is negative. So 3, you could have a sub n is negative and n is even. So that would be like y equals minus x squared. In that case, you would have both sides fall. And 4, you could have a sub n is negative and n is odd. And in that case, your left side rises, but your right side falls. So those are the 4 cases. So anytime you talk about n behavior, you just have to assess those 2 things, the number in front of the leading term, and then also the degree, whether it's odd or even. And in this case, like I said, we're looking at the 2 in front of the x to the 5th. That's positive. We're looking at the 5. That's an odd number. So that's why we know it falls left and rises right. It's case 2 from what we just wrote down. Okay, so then we get to the problem of intermediate behavior. So intermediate behavior, what we understand from it is primarily dictated by the zeros. So the zeros are when you write it out in fully factored form. So if you look at this example here, number 4, we have 2 zeros. They're basically the numbers you would plug in for x that would make the factor 0. So 3 minus 3 would be 0. So 3 is one of the zeros. And negative 6 is the other 0, because negative 6 plus 6 is the 0. Then after that, we talk about the multiplicity. So the multiplicity is the power that appears next to the factor. So in this case, we have 2 zeros, 3 and negative 6, and the multiplicity of each 0. For the first one, 3, it has multiplicity 1. That's the power of x minus 3. And negative 6 would have a multiplicity of 3. because that's the exponent next to the x plus 6. So the intermediate behavior is essentially completely determined by the multiplicity. So if the multiplicity is even, it bounces off the x-axis and turns around. If it's odd, it touches the x-axis and crosses. So each of these have a multiplicity of 1, which is odd, and 3, which is odd. So we know that it's going to cross the x-axis at 3 and also at -6. So that's the story for the intermediate behavior. So if, say, x equals c is a 0 of a polynomial, the multiplicity, so i.e. The power of the factor, or the exponent of the corresponding factor, determines the behavior. So, if the multiplicity is even, the graph touches the x-axis and turns around. And if the multiplicity is odd, the graph crosses the x-axis. So, in this case, we know it's crossing at both of these. I'm sure we'll have an example where it's not. As we said, the zeros were 3 and -6. So that's the first question. The second question is there are 2 zeros. The multiplicity of the largest zero, so the largest zero would be +3. 3 is bigger than -6. It has a multiplicity of 1. And the multiplicity of the smallest zero is 3. Now that's kind of weird wording, but you'll just have to kind of get used to it. It's just so they can't give away the answer. Determine the behavior at each zero. Well, we know it crosses at each zero because the multiplicity of both zeros is odd. Okay, so for one like this fifth question, we actually have to do it all ourselves. So the polynomial that they give us is not factored, so our first job is to factor it, and then we can apply the rules that we just learned for end behavior and intermediate behavior and all that jazz. So example, what are the instructions roughly here? So determine intermediate behavior for f of x equals x cubed minus 32x squared plus 256x. Okay, so the first thing we want to do is factor this. We know we can take an x out. So that leaves us with x squared minus 32x plus 256. And if you know your squares, this factor is really easy, right? 256 is 16 times 16. It's also one of those numbers that come up if you work with computers a lot, right? It's one of the memory things, right? Because computers operate in a binary structure. Their electronic circuits are determined by on-off switches, so those are two possibilities. So the memory scales by factors of 2. So 256 is a power of 2, right? It's 2 to the 8th, something like that. Right, if you hear like a gigabyte, right? A gigabyte is not actually 1,000 megabytes, it's really 1,024, right? It scales in that structure, so you have, right, 256 megabytes times 2 is 512, times 2 again, you have 1,024. So a lot of times we think in a base 10 system. Why in a base 10 system? Because we have 10 fingers, so we invented 10 symbols to write numbers. The Arabic numerals, 1 through 9 and 0, those are our 10 symbols we use to represent numbers. So we tend to think that way, although you really only need 2 symbols to write numbers. And a computer really just thinks with only those issues. Anyway, so back to the problem at hand. This is x, and then we have x minus 16 times x minus 16. So this is x minus 16 squared. So in this case, we have 2 zeros. So we have the zeros. We could think of the exponent, and then we have the resulting behavior. So the 2 zeros. A lot of people will forget if you just see an x out front. It could have a different power. It could be x squared, x cubed, x to the 35th, whatever. That's still a 0, right? If you plug 0 in for that x in front, that would make the whole thing 0. So one of the zeros is the number 0, and the other one is 16. So the exponent that is next to the x is 1, and the exponent with the x minus 16 factor is 2. So 1 is odd, so we get the cross behavior there, and then 2 is even, so I don't know, I guess we'll call this bounce. It touches the x-axis and turns around there. So the zeros are 0 and 16. So there are 2 zeros. So that's option B. The multiplicity of the smallest 0 is 1. And the multiplicity of the largest 0, which is 16, is 2. So we have the graph crossing at 0, and it touches and turns around, which I have said bounces at 16. Good stuff. Okay, the intermediate value theorem is essentially what's telling us kind of how the end behavior works. Essentially, one of the reasons that the end behavior is the end behavior, when we looked at the 4 cases and we said, why does it work? And we said, well, we only have to look at the biggest term. Why is that? Well, as you get farther and farther away from the y-axis, that means you're plugging in bigger and bigger numbers. And as a big number gets raised to a bigger power, that tends to dominate, right? If you think about, say, squaring a number, well, if you square 2, you get 4. That doesn't make it that much bigger. But if you would square 100, you would get 10,000. So squaring a big number makes it bigger faster. So that's dominating the behavior of everything. So the intermediate value theorem is really a property of continuous functions. And what it's telling us is, if you happen to know that a function is continuous, and polynomials, every single one of them is continuous, then really what it's saying, there's a lot of ways to kind of think about this, but so the intermediate value theorem. The intermediate value theorem, like I said, is really a property of all continuous functions, but it applies specifically to polynomials because every polynomial is a continuous function. So you can kind of think of it, I don't know, there's lots of ways to make analogies here. But imagine that, I don't know, you live here and you want to go to some store here, and there's a set of railroad tracks that is in between there, right? And we don't have any weird games where you're flying an airplane or something like that. Like you're just walking on foot, let's say. Now, if you want to go from here to here, basically the only way you can do that is crossing the set of railroad tracks, right? So at some point you're going to cross them. Well, this is what the intermediate value theorem is essentially telling us. It's saying if you have a continuous function and you know that it has a negative y value and a positive y value, at some point it's going to cross 0. That's all the intermediate value theorem really says. So, given a continuous function f of x, if f of a is less than 0 and f of b is bigger than 0, then there exists a value x equals c such that f of c is equal to 0. Right? So in this case, we would know some dot a where it's less than 0, some dot b where it's bigger than 0. So there exists some point where it has to cross that line that represents 0. Now, it doesn't exactly tell us where it is. This is a so-called existence theorem. It doesn't construct the value where it happens to be 0. But let's see how it applies in this example that they're giving us. So, example, we could use the IVT, intermediate value theorem, to show f of x equals 4x cubed minus 5x minus 2 has a 0 between x equals 1 and x equals 3. So this is like a weird thing. It's like a culmination of math and spelling. If you happen to like both things, then maybe you'll find this interesting. If you like neither, then I'm sorry, this might be the least interesting thing you've ever heard. But there are when you say it has a 0, if I were to write zeros versus zeros, what do you think about that? Is one of those spellings correct and the other one is incorrect? I've seen them written both ways, right? In my dealings as a mathematician, and I always wondered, well, what are we talking about here? I never saw either one of them show up on like a spell check as being incorrect. Now, why is that the case? Who would write, so just show of hands real quick, who would write zeros on the left? Who would write it that way? Okay, so 3 people. Who would write it zeros with an E on the right? You do both? How do you choose which one to use?
It just depends on how much I feel like writing, I guess.
Yeah, okay. So they actually mean different things. How is that possible? Well, one is a noun and one is a verb. So when we're talking about 0 in this context that we're currently talking about, a 0 means a place where the graph hits the x-axis, right? So if your graph hits the x-axis 3 times, that function has 3 zeros. Hence, it's a noun, right? So the correct plural noun form of zeros is on the left, zeros. But you can also talk about like dialing into something. So you can zero in on the answer. So something that zeroes in, as in honing in or dialing in, would be a verb, and that would be the zeros on the right. So both of them are real words, but they actually have two different meanings. And a lot of times, in absent of context, you might forget that. So that's my interesting confluence of grammar and mathematics. That I don't know. You might find interesting, or you might find stupid. But I may be one of the rare mathematicians that. So when I went to college, I majored in math, and my minor was English. So a lot of people think, math and English are opposites, but I like both. And interestingly enough, my sister is an English teacher, while I'm a math teacher. Okay, so how do we apply the intermediate value theorem? The only thing we really need to check is we need to plug in both of those numbers and make sure one of them comes out with a positive y value and the other one comes out with a negative y value. And if that happens, because we know this is a polynomial, it's continuous. So it'll have a 0. So we just plug in both numbers. So f of 1 is 4 times 1 to the third power minus 5 times 1 minus 2. So we get negative 3. So that's less than 0. Then we have f of 3, which is 4 times 3 to the third minus 5 times 3 minus 2. So we get 4 times 27. So what is that? 108 minus 1791. Is that right? Double check that. Is that right? Let me do it on the calculator. You can get out the calculator and see. I don't trust my mental math in night classes. 4 times 27 minus 15 minus 2. Yeah, 91. Okay. Well, it's still trustworthy. So, by the IVT, f of x has a 0. So how do we answer this question? How does the computer want it framed? F of 1 was negative 3, which is less than 0. And f of 3 is 91, which is bigger than 0. So there we go. Okay, this one is the same. Okay, so it looks like for this one we're using kind of all the parts that we've learned so far. So let's go ahead and do this. We're going to find the end behavior and the intermediate behavior. So example. So basically sketch f of x equals x to the third plus 2x squared minus x minus 2. So when we have such a problem, we first need to determine the end behavior. So remember, the end behavior, we look only at the leading term, which in this case is x cubed. The number in front is 1, so that means the a sub n is positive. And the power of the leading term is 3, which is odd. So positive and odd, what kind of end behavior does that mean? That means falls left and rises right. If you scan back in the notes. So that is falls left and rises right, choice C. And then the X-Intercepts, so we find the X-Intercepts by factoring. So we know x cubed plus 2x squared minus x minus 2. So to factor this one, what we do is we factor by grouping. So that's one of the techniques we learned. So you group the first two factors and then the second two factors. So the first two factors have a common x squared that you can take out. So if we take out x squared, we're left with x plus 2. And then from the minus x minus 2, we can take out a minus 1. And then we get x plus 2. So this factors into the x squared minus 1 times the x plus 2. And then x squared minus 1 will factor from difference of squares, right? So we have x plus 1, x minus 1, and x plus 2. So that's the fully factored form. So that tells us all three zeros. And I'm sure they will ask us about intermediate behavior shortly. So we can kind of do our intermediate behavior chart. So we have our 0, our exponent, and our behavior. So what are the zeros? We have minus 2, minus 1, and plus 1. Remember, those are the numbers you would plug in for x that would make 0. The exponent of each one is 1, and so we cross at every 0, because the exponent is always an odd number. When the exponent is even, that's when we bounce. So our x-intercepts are -2, -1, and +1. Which intercepts does it cross? It crosses at all three. Comma 1. Which intercepts does bounce? Doesn't do that at any. Find the y-intercept. How do you find the y-intercept? Well, you plug in 0 for x. So if you plug in 0 for x, those first three terms would go away. The x cubed, the 2x squared, and the minus x, those all go away. And we're just left with that minus 2 sitting there at the end. So the y-intercept is minus 2. Symmetry. It will only have symmetry if all of the terms are odd or all of the terms are even. So this has odd and even terms, so there will be no symmetry. If they're all even terms, it will have y-axis symmetry. If they're all odd terms, it will have origin symmetry. So this one is neither. Then they're going to make us graph it. So how do we graph it? Well, we pick this polynomial shape. Two polynomial shapes based on the end behavior. We know one side's going down and one side's going up. So we pick this guy. And then basically we're just going to hit the... We know 3 x-intercepts and 1 y-intercept. So we can just click those 3 places. We know it goes through -2, -1, and +1. And we also know it hits the y-axis at -2. So that gives us our shape. All right. All right. This is another one of the same type. Let's go ahead and go through it. Again, I'll just kind of hit the high points, and then after that, I'll leave similar questions to you. So our job here is to sketch f of x equals x to the 4th minus 16x squared. So end behavior, let's start there. So our leading term in this case is x to the 4th. So the number in front is 1 and the power is 4, which is even. So we are positive and even, which is both sides go up. So both sides up. So rises on both sides is what we're looking for. Rises left and rises right. The intercepts, this is where we have to factor again. So we've got x to the 4th minus 16x squared. So first we can pull an x squared out, and that will leave us with x squared minus 16. and then x squared minus 16 is a difference of squares, so that will factor into x plus 4 times an x minus 4. Now we are ready for intermediate behavior, so we can write the intermediate behavior chart. So we have our 0, our exponent, and then the resulting behavior. So we have 3 zeros here. Don't forget x squared corresponds to a 0 of 0. So we have 0 minus 4 plus 4. X has a power of 2. The other factors each have a power of 1, which means we're going to bounce off at 0, and we are going to cross at minus 4, and we'll also cross at positive 4. All right. Pretty easy. You just got to get in the habit of doing things a lot. That's maybe one reason why math is difficult for some people. If you don't repeat it enough, it just doesn't get absorbed into your bones, and it's harder to synthesize the big picture ideas. There's a lot of kind of smaller things you have to do to grasp the bigger picture. Okay, so the x-intercepts, minus 4, 0, and 4. And then at which 0 does it cross? At minus 4 and positive 4. And where does it bounce? It bounces at 0. Find the y-intercept. Well, if you plug 0 into that, both terms have an x, so plugging in 0 for x results in 0. Does that make sense? 0 to the 4th minus 16 times 0 squared comes out to 0. So the y-intercept is just 0. The y-intercept of a polynomial is always its constant term. So whatever regular number you see there not multiplied by x, that's going to be the y-intercept. So because this one has no constant term, the y-intercept is 0. Symmetry, notice that this one we have both terms even. So the power, the exponents there are both even. So when you have an even function for polynomials, it means all the powers are even. That has y-axis symmetry. When it's odd, meaning all the powers that you see are odd, it would have the origin symmetry. If you have a mixture of the two, it's not symmetric. So this one, even, we get the y-axis symmetry. And then what is the graph? We actually don't have to input it here. We know it's going to bounce at 0 and cross at positive 4 and negative 4. That one doesn't bounce at 0. B doesn't cross at positive and negative 4. C is exactly what we're looking for. Crosses at negative and positive 4 and bounces off at 0. And D doesn't cross at plus and minus 4. So C is our choice for picking the graph. Okay, so now we get into dividing polynomials. So we can talk about two methods. There's long division, and then there's also synthetic division. So synthetic division is a shortcut method you can use when you're dividing by something of the form x plus or minus a number. So synthetic division is a shortcut that works when you're just trying to where you only have to worry about the coefficients, let's say. So again, it's kind of hard to explain without just going through some examples. So we will show you in this example. So divide x cubed minus 3x squared minus 2x plus 2 divided by x plus 1. Okay, so the way I like to do it, I like to put, so the thing you're dividing by, the x plus 1, you first ask yourself, what is the 0 of that? And again, that's the number that you would plug in for x that would make it 0. So in this case, that would be minus 1. So I write minus 1 up here in the corner. And then on top, I'm going to write all the coefficients of the other polynomial. So I have a 1, a minus 3, a -2, and a +2. And then I write a line like this, and then this is where the magic happens. So the first step is to just bring down the first number. Now, whenever you get a bottom number, or a number in this bottom row, you multiply it with the number in the corner, and then you write it above the line below the next number. So I'm going to take 1 times -1, and I'm going to write that result -1 here. Now I'm going to add the numbers in that column. -3 plus -1 makes -4. Now I multiply -4 by this -1 and bring that up to the next position. So that's +4. Now I add that column. -2 plus 4, +2. Now I write this number times -1, and I write that in the next position, and then I add the column. And now I'm done. So I've done the division. What is that telling us? Well, this is the remainder. This is the constant. This is the x term. And this is the x squared term. And it can be longer than this, and you would just keep adding terms, right? So if I had one more, it would be the x to the third term, then the x to the fourth term, and so on. So the result of my division here is x squared minus 4x plus 2 plus my remainder over the thing I'm dividing by, which is x plus 1. That's how I get the result up here. So that's synthetic division. Really nice, really easy. It only works when we're dividing by this, something of the form x plus or minus a term. That is the most common task, however, because it allows us a way to find zeros when we talk about the factor theorem and remainder theorem. So we have x squared minus 4x plus 2, and then we just put a 0 up here in this second box. Again, this one we can do a synthetic division problem. In the help, they say use long division, so they're going to show you a different method where you have to keep all the x's built in. But as long as we're dividing by something of the form x plus or minus c, we can use synthetic division. I used to say, from kind of the perspective of, well, all division is really long division, so if I just teach long division, I never have to teach synthetic division. But as you do it more, and you realize it's the most common case, then synthetic division becomes a nice tool. So I've adapted, and now I am a proponent of synthetic division, whereas in my younger days I would always just go through long division. I understand my old point of view, but I like synthetic division now. So as you get older, your tastes mature, I suppose. Or change. Who can say? Maybe they get worse, right? Because when you're younger, you actually have more active taste buds, and then it's just an analogy. I'm just being silly. Okay, so this one is a little more interesting in the sense that we have some terms missing. So how do we deal with missing terms? Well, the number on the bottom is still the same, right? X minus 2 happens to correspond to the number 2. That's the 0. So we're going to plug that in. But what do I mean missing terms? Well, the thing on top that we're dividing into, we have 4x to the fourth, and then we jump to x squared. So there's no 0 term. Also, there's no constant term. So I'm going to fill those spots in with zeros so that I account for them so that everything is lined up. So if there's spots missing, put zeros there. Does that make sense? So I'm going to put a 2, then a 0 for the missing spot, then the minus 4 that's next to the x squared, then a 4 next to the x, and then a 0 for the missing constant term. That's how I'll know I'll have the appropriate number of steps and won't miss anybody. So how does this work? I bring down the first guy. Then I multiply 2 with the 2 in the corner. 4, I write that result there. 0 plus 4 makes 4. Then I do 2 times 4, which gives me 8. Negative 4 plus 8 is 4. 4 times 2 is 8 again. 4 plus 8 makes 12. 12 times 2 is 24. And then I add 24. And again, what does this result really mean? Well, it means I have a remainder, a constant, an x squared, and an x cubed term. So my result here should be 2x to the third plus 4x squared plus 4x plus 12 plus my remainder of 24 over the x minus 2. And again, that's kind of like if you think about the how it worked with regular numbers. Let's say you were doing 15 divided by 7. What would happen? It would go in twice. 15 divided by 7 is 2 with a remainder of 1, which really means 15 over 7 is the same thing as 2 plus 1 over 7, right? So this is kind of like the same thing as a mixed number when we write this result as a polynomial plus a remainder divided by the thing you were dividing by. Okay, again, we're back to another synthetic division example. We'll maybe do one more of these, just to keep us in the habit. And again, if you want more practice with this, I know I do the module lectures, but I host them all on YouTube, and I probably have like, I don't know, 100 math videos on there. If you want to search my channel for more synthetic division practice problems, I have other videos on synthetic division. So a lot of times you can search my channel and find more videos on certain topics other than our module-specific videos. So I will point to that as another point of reference. Also, I think our textbook has some videos with it if you ever want additional examples. So again, we just want to divide by our favorite method, synthetic division. So, minus 4 goes in the corner. And then we have 4, 5, and minus 10 on top. Make our line. Bring down the 4. I feel like I need to draw that arrow for some reason. But I think other people probably draw it differently, but I don't know. You could Google pictures. 4 times negative 4 is minus 16. Add, we get negative 11. Negative 11 times negative 4 is positive 44. If you add those, you get positive 34. And so what is this telling us? This is telling us our answer is 4x minus 11 plus 34 divided by x plus 4. And that's the end of the problem. So, I don't know. Once you get the hang of synthetic division, it's kind of fun. Okay, so more synthetic division. I think we can skip that. Okay, this is the remainder theorem. So this is another consequence of synthetic division, but I'll write down what the remainder theorem says. So let's say if p of x is a polynomial, and P of X is divided by, it's probably a better way to say this. Let's say X minus C. The remainder is equal to P of C. So rather than plugging C into the formula and doing the computation, you can also just do the synthetic division. So you want to see a proof of that fact? The proof is pretty easy. So if you take a polynomial and you divide it, then what's happening? You have the thing you're dividing by, which is X minus C. It's multiplied by the quotient polynomial, and to that you add the remainder. So what happens if you plug in C? P of C would be C minus C times Q of C plus your remainder number. Well, C minus C is 0. So this is just equal to 0 plus R, which is equal to R. So our remainder is equal to P of C. So that's it. Pretty easy proof. But again, this allows us to do more synthetic division. And synthetic division is fast and easy, so we like it. So if you have this example, we have f of x is 5x cubed minus 11x squared plus 8x minus 7, and we want to compute f of 1. That's all we need to do is do the synthetic division with 1 in the corner. Note that 1 corresponds to the 0 x minus 1, or the factor x minus 1. So we don't have to change the sign there when they phrase the problem this way. So then we write our numbers on top. 5 minus 11, 8, and minus 7. And then we just do the synthetic division. And the answer to this question is just whatever the remainder turns out to be. So we bring down the 5. 5 times 1 is 5. Negative 11 plus 5 is minus 6. Minus 6 times 1 is minus 6. Add, you get 2. 2 times 1 is 2. Negative 7 plus 2 is minus 5. So this remainder is our answer right here. So this tells us that f of 1 is exactly equal to minus 5. That's it. Okay, and then we can also use this to factor. So in general, we can't solve cubic equations, but if we know one of the zeros, we can use synthetic division to rewrite that polynomial, right? So this says solve x cubed minus 13x squared plus 47x minus 35 equals 0. Given that 1 is a 0. So we know that 1 is one of the zeros. So we can divide using synthetic division. That means x minus 1 would evenly divide into this polynomial. So if I put a 1 here, and then I go, okay, 1 minus 13, 47 minus 35, then I do the synthetic division, bring this guy down, I get 1, 1 times 1, then I have negative 12, negative 12 times 1 is negative 12, then I get 35, 35 times 1 is 35, and then I get 0. How did that help me? Well, that tells me how to factor this thing. It is telling me, in fact, that x cubed minus 13x squared plus 47x minus 35, it's equal to the thing I divided by, x minus 1, times the stuff left over, since there's no remainder, right? If it goes in evenly, there's not that plus an extra term. So what's left over? I'm left with an x squared minus a 12x plus a 35. And then I can use the shortcut on the remaining polynomial to divide that, right? What two numbers multiply to positive 35, but add to negative 12? Well, that's going to be negative 7 and negative 5. So this will factor into x minus 1 times x minus 5 times x minus 7. So now I have my answer, right? The 3 zeros are going to be the numbers you would plug in for x that would make each factor 0, right? So they would be 1, 5, and 7. Okay, the rational roots theorem. What it does is it doesn't solve a problem for you, but it tells you if you have solutions that happen to be rational numbers, it tells you a list of things to check. So, how many am I at? 50%. So let's write down the statement of the rational roots theorem and see how to apply it. So suppose p of x is some polynomial, and we'll write it down in the complicated looking form again, a sub n, x to the n, plus a bunch of other terms, plus a sub 0. That's all we really care about is the leading coefficient and the constant term. So the statement says all rational zeros right, and this is zeros without the e, because this is the noun, of p of x have the form, let's say, I want to use p, but I've already used p. So let's say m over n, where m is a divisor of a sub 0 and n is a divisor of a sub n. So it gives us a list. It tells us all the possibilities for the top of the fraction, all the possibilities for the bottom of the fraction. So, in this example, so list all possible zeros of f of x equals 5x to the 4th minus 4x cubed minus 8x squared minus 10x minus 10 according to the rational root theorem. So how does this go? Well, my possible numerators are what? My possible numerators are they the divisors of minus 10 at the end or the divisors of 5 in front? Well, the number on top is the possible numerators are the divisors of the constant term. So these are all the numbers that could go evenly into 10. So what can go into 10? Plus and minus 1, plus and minus 2, plus and minus 5, and plus and minus 10. Yeah? Then my possible denominators are the numbers that could go at the bottom of a fraction. Those are the divisors of the number in front of the polynomial, which is 5. So there's 4 of those, plus and minus 1 and plus and minus 5. So then from those two, we make the possible zeros. So this is our actual answer. The possible zeros are all the things you could put on the top of a fraction from that list and all the things you could put on the bottom. So if you put everything over 1, the top list repeats itself. So you're always going to have the top list again, plus and minus 1, plus and minus 2, plus and minus 5, plus and minus 10. And then you could also have 5 as the denominator of your fraction. So you could have a fifth, you could have 2/5. 5 over 5 is 1, that's already there. 10 over 5 is 2, that's already there. So we also get to add the numbers plus and minus 1/5 and plus and minus 2/5. And that's our list. What list does that match up with? It looks like list D. There we go. So the rational roots theorem gives you a way to, if you have, you can have roots of a polynomial that are not rational though. Right, like x squared minus 2 equals 0. The answer to that equation is, one of them is the square root of 2. That's not a rational number. So it won't always give you the answers, but if it does have a rational answer, you could have this test, you could plug them all in. If one of them is 0, and then you found it. Okay, so we're going to go through one of these. These are kind of long. You list all the roots. You test them. Of course, nowadays with machinery, we have numerical tools that will help us, right? So the rational roots theorem in that sense feels a little bit outdated if we want to cheat, right? If we want to cheat, what can we do? We can just graph the function and see where it hits the x-axis. Then you know the answer. Does that make sense? So in that sense, the rational roots theorem is kind of like outdated technology. But we still have the question here, so we'll go ahead and do it. So in this example, we'll try and skip the steps, but so we have the function f of x equals x cubed minus 5x squared minus 9x plus 45. So let's list the possible zeros. Let's try and just do it all in one step. If that's confusing, please let me know. Again, the tops of our fractions, well, that's all it's going to be, right? This is an easy example for the rational roots theorem because 45 is the number at the end. So we're just looking for 45 because what's the number at front? The number in front is just a 1. So if the number in front is 1, then the only thing that can go on the denominator is a 1, which makes all the possible zeros whole numbers. So the only possible zeros are going to be things that go into 45 evenly. So we just need to list the divisors of 45, which are plus and minus 1, plus and minus 3, plus and minus 5, plus and minus 9, plus and minus 15, and plus and minus 45. So still quite a few. So we have to list all these on the deal here. You can use the plus and minus button though, so that kind of saves you a lot of work. And then it says use synthetic division, or you could plug in the numbers either way. From the remainder theorem, we've seen that those are equivalent. Let's try to do one that we know is going to work. What do we know is going to work, and how do we know? Well, we can see that 5 is going to work, for instance. So let's choose 5. If you guess poorly, it will take longer. Again, so how could we cheat? We could cheat by, say, graphing it, right? So if we want to just find the answers right away, we can just graph it, right? F of x. So Desmos.com, great graphing utility. What was it? X cubed minus 5x squared. And then, was it minus 9x plus 45? I think. Minus 9x plus 45? Yeah, so we can see our answers immediately. The answers for the equation are going to be -3, +3, and +5. Okay, so that's how you can kind of use the graphing calculator to cheat on this problem. But let's go ahead and do it right the first way through, and then if you decide that it's not worth your time, then that's up to you. But one rational zero of the function is 5. How could you test that? How do they want you to do it? They really want you to do the synthetic division. So we could do a 5, and we could list the numbers 1, -5, -9, and 45. And we just want to make sure the remainder is 0 here. So bring down the 1, we get a 5, that makes 0, 0, -9, -45, and then we get a 0. So that works. And that tells us, in fact, that x cubed minus 5x squared minus 9x plus 45, this factors into x minus 5 times x squared minus 9, which we know factors into x minus 5, x plus 3, x minus 3, which is how you get all the answers from factoring. But you could also do it by graphing. So -3, 3, and 5. And that's it. So the next one is a similar question. Again, you can go ahead and graph it, or you can do it with the synthetic division and factoring. Up to you. So we'll skip this one. Yes? You have to guess a number from the list. I saw that it factored by grouping, so I mentally did the problem and chose wisely, and then that way I didn't have to guess wrong a bunch of times. But your odds are not good if you're guessing at random, right? Because how many possible zeros are there? 1, 2, 3, 4, 5, 6 times 2, 12. So there's 12 possible guesses up there. Only 3 of them work. So if you were guessing at random, right, you only have a 25% chance to guess a 0. And if you guess wrong, then you just have to guess something else and try again. So that's why it could be frustrating. If I picked something like, say, 9, and I did the synthetic division, I would end up with a remainder that's not 0. Then I just have to pick another one and go until I eventually find one that's 0. Then it'll factor into something smaller, which I should know how to factor. Yeah. No, it's a good question. That's why it's not the best system. It feels like working with outdated technology a bit, but for a long time this was a very good thing to use. Again, we said this one is the same type of question, and so is this one. And so is 20. Okay, so the last two questions are weird. This is known as Descartes' Law of Sines. This is on the syllabus here. I don't ever teach this it's hardly ever on the syllabus, so this one is quite a rare theorem. So we'll go over this one, but probably you'll forget this. It's kind of like a bizarre rule. I don't even know if I can state it properly off the. So Descartes' Law of Sines, and this is Sines GNS. Do we know who Rene Descartes is? The French mathematician and philosopher. So, the XY plane that we draw everything on, that's named after him. Have you ever heard Cartesian coordinate plane? That's his name. So, Rene Descartes, named after him. He also, in philosophy, was famous for his skepticism, Cartesian skepticism, but also cogito ergo sum. You've probably heard of that before. Does anyone know what cogito ergo sum means? It's Latin. I think, therefore I am. He is the philosopher that said that. So. I have one Descartes joke if you want to hear it. So, it's very bad, but it's based on what I just told you. So, absolutely you won't get it if you don't know that Rene Descartes said, I think, therefore I am. So, keep that in your head. So, Rene Descartes walks into a bar, and the bartender asks him, do you want a beer? And he says, I think not, and vanishes. That's it. So, alright. Now we have to get back into Descartes' Law of Sines. So, oh, it's really bizarre. It's like, okay, it's like, so, it's like if you do f of x and f of negative x, you count the number of sign changes, and then the number of zeros it can have is that number or an even multiple less. Really bizarre. So we're going to have to look, maybe it'll say on the question help. I can't, the statement of this Descartes' Law of Sines is bizarre. We might have to go to the textbook for me to, I just don't want to misstate it. But this is completely forgettable. It's just exotic. It doesn't come up a lot. But it is kind of interesting. So it'll be at the very end of the section, I'm sure. There you go. There's, that's not him. That's Tartaglia's formula. He was an Italian mathematician. So we did rational roots. We're looking for Descartes' Law of Sines. Descartes' Law of Sines. Here we go. There's Rene Descartes. And this zoom feature is not great. Okay, so you count the number of sign changes, then it's however many less. So here's the rule. See, it's a very kind of hard rule to see. So the number of positive real zeros is either the same as the number of sign changes of f of x, or less than the number of sign changes of f of x by a positive even integer. See, I said it was an even multiple less. That's what I meant. The number of negative zeros is the same as f of negative x, or less than the number of sign changes of f of negative x by a positive even integer. Okay, so a little bizarre. Let's go back and see if we can. I'm not going to write that down because it's a lot to write down. We'll just see if we can apply it properly. So I'm going to erase. Well, maybe we can do it. So positive zeros. We'll try and do a positive number of zeros. So sign changes in f of x or even multiple less. Negative zeros, it's the sign changes in f of minus x or even multiple less. Oh wow, did I? Oh, that's for this last one. So let's do this one, then go backwards. I got the cart before the horse there. I misremembered what problem we're on. So, Descartes' rule of sines. So f of x here, how many sign changes do we have in just the regular function? 0. There are no sign changes, right? The number in front of x cubed is 1, 6 is positive, 5 is positive, and 7 is positive. Those are all positive, so there are no sign changes. So that means there are no possible positive real zeros. So 0 for the number of possible real zeros. What about the negative real zeros? So let's do this example next to it so we remember. Example. So let's say f of x equals x cubed plus 6x squared plus 5x plus 7. So no sign changes. So no positive zeros. Okay, now we have to do f of minus x. So that would be minus x cubed plus 6 times minus x squared plus 5 times minus x plus 7. So that's minus x cubed plus 6x squared minus 5x plus 7. So how many sign changes do we have here? Negative to positive, 1 sign change. 6 to negative 5, 2 sign changes. Negative 5 to 7, 3. So 3 sign changes. So this means we have 3 or 1, right? Let's say we had 11 sign changes. You could have 11 or 9 or 7 or 5 or 3 or 1. That's what I mean by an even number less. So 3 or 1 negative zeros. So here we can just type 1, 3. Get that answer. All right, so that's 22. Let's go back to 21. 21, find an nth degree polynomial satisfying the conditions. So this does not deal at all with Descartes' Law of Sines. So find a polynomial satisfying, and then we're done after this one. N equals 4. I and 5i are zeros, and f of minus 1 equals 104. Do you guys remember where I comes from? What is that an equation to? So square root of negative 1, which comes from the equation x squared plus 1 equals 0. Remember that? Because if you would solve x squared plus 1 equals 0, you'd have x equals minus 1 and then the square root of that. So I comes from x squared plus 1 equals 0. So basically, in this one, I is a root, just to remember, I is a root of x squared plus 1 equals 0, which would mean 5i, what do you think 5i is a root of? X squared plus blank equals 0. Plus 5, yeah. So 5i is a root of x squared. Oh, no. Wouldn't it be 25? Because you have to take the square root of it. Yeah, so x squared plus 25 equals 0. Right? If you would solve x squared equals minus 25. So x is plus or minus the square root of minus 25, which is x is plus or minus 5 times the square root of minus 1, which is plus or minus 5i. So for this one, we know our polynomial f of x has to equal some number a times x squared plus 1 times x squared plus 25. We know it looks something like that. So now we're going to use that last piece of information, f of minus 1 equals to 104, to figure out what that a in front is. And then once we've done that, we've got our expression. So if you plug in -1, f of x should turn into 104. So we get 104 equals a times -1 squared plus 1 times -1 squared plus 25. So 104 is equal to, this is a times 2 times 26. So 104 is 52a. So a is equal to 2. So long story short, our answer here is f of x is 2 times x squared plus 1 times x squared plus 25. And that's how we answer this one. They say simplify our answer, so I don't know if they want us to expand this. I hope not. I mean, it's not that huge of a deal, but it depends on how in the mood you are to FOIL. But they've not foiled our plans. All right. Okay, so are there any questions on any of this? So we covered a lot of ground today, but we have gone over all of Module 6, which was a big whirlwind on polynomials, how to find their zeros, how to look at their graphs, end behavior, intermediate behavior, synthetic division, Descartes' Law of Sines. So we'll finish there, and I'll get this posted if there are no other questions. Let me just stop the recording.